So we're going to go through the Combined Science Physics Higher Paper 1 from 2022 today. The first question is all about how we use energy resources to meet the demands for electrical power, and it's looking at the data from one day in 2020. So you've got your graph of information there. Now, the maximum demand for electrical power on that day was at 6 p.m. You've got to determine the percentage of the maximum demand for electrical power that was generated using gas. Now, we start off by, you need to look at what was happening at 6 o'clock. So you need to get your ruler and draw a line straight up. And from there, you need to collect your data. Now, the total demand for electricity at 6 o'clock was, again, you're going to draw a nice straight line with your ruler, was 30,000 gigawatts. So total demand equals 30,000 gigawatts. The other bit of data you need to know about is how much gas was produced at 6 p.m. So again, draw your line across, and that should come out as being 16,500. So gas equals 16,500 gigawatts. We now need to determine the percentage of the demand that came from gas, or was met by gas. So we then do 16,500 divided by 30,000. Of course, we're turning this into a percentage, so we need to multiply by 100. There's your second mark. You then put those numbers into your calculator, and you get an answer of 55%. 3 nice easy marks to start with, hopefully. And then 5.2, sorry, this is 1.2. UK government wants to reduce carbon emissions as much as possible. And which energy resources do we need to use less of to achieve this? So what we're really looking for are things like our fossil fuels. They produce our carbon dioxide. And if you look at your first option, coal and gas, they are both fossil fuels. So that's suggesting that's probably the correct answer. Just to check, well, gas is a fossil fuel, nuclear doesn't produce any carbon emissions. Wind and coal, well, coal does, but wind doesn't. And again, wind doesn't down there, and nuclear doesn't either. So our correct answer there is coal and gas, and make sure you tick that one. Now, this question, what is a network called of transformers and transmission cables which transfer power from our power stations to home? This is one of those things you just need to remember. It is the national grid. And that's the only answer you can give to get that 1 mark. Now we need to explain how using step-up transformers makes a network efficient. Now a step-up transformer, it increases the potential difference. So increase the potential difference, and at the same time, this causes the current to decrease. Now, if you have too much current running through the cables will heat up. So, in a way, the more current you've got flowing, the more heating you have, and then that leads to unwanted energy losses. So you're losing energy. By reducing the current, there's less heating of the cables, so less energy dissipates out into the environment, and we're just conserving energy. So it means that this is how our network's more efficient, because we have less energy losses to the atmosphere, or in terms of heating the cables. That is just wasted energy, and that's where your third mark comes from. So we're talking about less energy is dissipated. And then the next question, here we've got our 6 marker, and it's about writing a method. However, it's not just about writing a method, as we'll talk about now. So a student made measurements to determine the specific heat capacity of vegetable oil, and you're given the equipment to use. You have to describe how the student could use the equipment to determine the specific heat capacity of vegetable oil. The important thing here is you need to be explaining specifically how to use the equipment. So don't just say take the temperature. You need to say take the temperature with a thermometer. You need to talk about measuring the mass by using the balance. So you've got to be very specific with it if you want to get the full marks on this. Now, I'd recommend that you always bullet point methods. It makes it much easier for the examiner to mark. So the first thing is I would start off with talking about using the top pan balance. So use top pan balance to measure the mass of oil. The oil is in the beaker. So some of this might be very obvious, but you need to cover all these points. Now we need to record the temperature. I'm just going to abbreviate some of this. Record the temperature of the oil using the thermometer. So again, you're talking about how to use the equipment given. Then place the beaker of oil on the heater, and remember to turn it on. So we need to turn it on. So the heater is connected to the joule meter, which measures how much energy, just abbreviating it to E, is transferred to the oil. We then need to allow the oil to heat up, so I'd suggest that we go for once the temperature of the oil has increased by, let's say, 10 degrees centigrade, stop heating. And we need to record the number of joules of energy transferred. So the energy transferred on the joule meter. Now, at this point, we've got all the readings that we need. So don't forget, we've shown how to actually calculate the specific heat capacity. So we need to talk about using the formula. So put the values into the formula, and this is where you might need to use your data sheet. So energy transferred is mass times specific heat capacity multiplied by the change in temperature, and we use that to calculate the specific heat capacity, that's C. Now, just to finish this off nicely, we need to repeat this, well, at least twice. So we end up with 3 lots of data. Repeat this twice more to calculate a mean. If you include all that information in your answer, you're looking at 6 marks. But you have to be talking about how you used every piece of equipment. Now what you can do is, just to make sure you do this, is you could note down next to the equipment thermometer to measure temperature, to measure T, top pan balance, measure mass. What you'll find is that all this gets scanned by the examiner, so they will see that the notes you make kind of up here, the examiner will see and will give you credit if you've put something correct that you might not have included in your method. But try and get it into your method makes life a lot easier. Alright, next one. So, give one risk when using the equipment in figure 10. You're heating oil. So, burns and scalds are your most likely risks. Don't talk about the hot oil, that's a hazard. They want to know about the actual risk. So, make sure you are actually answering the question properly. Now the next question should be one of the easiest marks you're going to get here, because it's asking you to write down the equation linking energy transferred, power and time. And you'd actually have the formula sheet to help you do that. So remember, power equals energy transferred over time. P equals E over T. You can write it fully in words, or you can use the symbols. As long as you get it right, that's the important thing. Now in 6.4, or 2.4 in your case, we're now going to use that previous formula to do a calculation. Now, I'll always write that formula down again. Power is energy transferred over time. Now, we don't get a mark for that. However, we get a mark when we substitute the numbers. So any calculation, you need to be underlining what you've got. So we've got power in watts. We've got our energy transfer in joules. We need to calculate the time taken. So that's going to be our unknown. So we now just substitute the numbers we've got. Well, we've got a power of 50. So 50 equals 4,750 divided by T, our unknown. At this point, we've now got a mark, just by substituting the numbers correctly. Your second mark comes from rearranging the equation, starting to solve it. So we need to get T, so we end up with 4,750 divided by 50. If you put those numbers into your calculator carefully, you then get the third mark by calculating that the answer is 95 seconds. And then, next part of the question, we're looking at we're relating the oil to the deep fat fryer. So the vegetable oil is heated by an electric heating element, and the food's cooked in the hot vegetable oil. That doesn't really help you in terms of answering this question. Now the deep fryer contains an electrical component to monitor the temperature of the vegetable oil. Now here below you've got a graph showing how the resistance of the electrical component changes with temperature. So what electrical component is used to monitor the temperature of the vegetable oil? Now there's a clue up here, this bit here. How does the resistance change as the temperature changes? Well, there's a certain type of resistor involved for that. We're looking at a thermistor. And then 6.6, we've got our electric heating element in the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. So we've now got figure 12, and it shows how the temperature of the vegetable oil changed after the deep fryer was switched on. Determine the resistance of the electrical component when the electric heating element automatically switched off. Now the first thing you need to do is the fryer is clearly turning off when the oil doesn't get any hotter. If you read that number off the graph, that happens at 160 degrees centigrade. Now if that's the only thing that you've actually done to answer this question, you actually get 1 mark. However, there's 2 marks available. We now need to take that 160 degrees centigrade, then use figure 11. We find 160 on the x-axis, and we draw a nice straight line up to the curve. Where it hits that line, we then need to draw across, again with your ruler, and you need to read the scale carefully. That should come out at 240. So the resistance, and your 2 marks, you're going to get 250 ohms. Not quite sure why they give you so much space to write, because you're actually going to draw on your graph. And again, drawing on the graph, your examiner will look at that, and that's where you'll get your marks from. So 1 mark for establishing 160 degrees centigrade, the second mark for getting 240 ohms of resistance. Well done if you got that one. And then the final part of this question, some of the chips were put in the deep fryer, and it's asking about why is this a physical change. Now, there are some correct facts in this list you got, but you have to pick the best answer. So all water can change to steam. Well, that's true, but it doesn't necessarily explain why it's a physical change. No chemicals are involved when water changes to steam. Well, water is a chemical, so we can ignore that one. The change from water to steam can be detected visually. That's true, but it doesn't necessarily mean that we've got a physical change. So that's not a particularly great answer. The water will recover its original properties if the steam is cooled. This is just a very wordy way of saying if you cool down the steam, it turns back to water. That is a physical change. So it's actually the final answer on that one. That's the end of that question. Hopefully you got 15 out of 15 on it. So with question 3, we've got a trampoline with a child jumping up and down on it, and really this question is all about the springs and the energy related to that. Now first of all, we've got position A shows the child's maximum height above the trampoline, and then position B shows the lowest position reached by the child when landing on the trampoline. Now we need to describe the changes to the stores of energy of first of all the child, and then the springs, and then the surroundings as they move from position A down to position B. So we need to talk about each part of this in turn. Now what happens to the child? Well, they start off high up and they end up low down. So straight away you should be thinking about the gravitational potential energy. I'm just going to abbreviate that E for energy. So of course that is decreasing as we drop down. However, at the same time, because the child is moving, they're moving downwards, it means that their kinetic store of energy, the kinetic store has gone up. Obviously that's until it reaches position B, when it will go to 0, because the child is now stopped. There's our first 2 marks. And then we need to look at the springs. Well, at position A, our springs will be unstretched, and then at position B, our strings are stretched. So that means we're looking at the elastic potential energy. So the elastic potential energy has gone up because we've now got energy stored in those stretched springs. That's worth another mark. And then finally with the surroundings, because the child is moving, the trampoline's moving, the springs are moving slightly, that's going to cause a little bit of friction with the surroundings, with the air and the materials. So it means that our internal or thermal stores of energy are increasing. So energy, the other acceptable answer here is that you could say that the energy is dissipating into the surroundings. So that's where your 4 marks are going to come from on that one. Now, this next question is a great question if you like your maths, and it's worth 5 marks. So these are good questions to practice because they are, once you get your heads around this style of question, they're easy marks to get. So we've got the child at position A, and each trampoline spring is stretched by 0.056 of a metre. We're given the elastic potential energy of the spring at this point of 4.9 joules. We've got some information about when the child is at position B, the elastic potential energy of each spring increases to 8.1 joules. Calculate the extension of each spring when the child is at position B. Now it's telling you to use the physics equation sheet, and that's good advice because what you need to look for is a formula for calculating elastic energy. Now elastic energy is half multiplied by the spring constant, which is K, multiplied by the extension squared. So the first thing we need to try and calculate here is we need to know what K is. So substitute in the numbers that we've got at position A. So remember, this is just looking at position A. So the numbers are 4.9, 0.056. So put those numbers in there. 4.9 equals 0.5 multiplied by K, which is our unknown, multiplied by 0.056 squared. So just be careful with how you're using your calculator. And then you just need to solve that equation. So you should end up with K equals 3,125 newtons per metre. So that is a spring constant calculated. Now the spring constant, its name suggests, is a constant. It's always going to be the same. So we now need to use that information to calculate how far the spring extends at B. So again, we've got the same formula to use, or the same formula to use to substitute numbers in. This time we've got 8.1 joules of energy. So we've got 8.1 equals 0.5, and it's multiplied by our spring constant, which we've calculated to be 3,125, and that's multiplied by the extension squared. We now need to solve that, so you end up with the extension squared equals 8.1 divided by 0.5 multiplied by 3125. Once you've worked that out and found the square root of that number, you end up with an extension equals 0.072 meters. So I just need to fill that in there. There's not a huge amount of writing in that, but that's worth 5 marks. So like I said, practice the calculations because these are good marks to pick up. 2.3. As a child bounces on the trampoline, the child does work. What is the work done by the child equal to? Well, it's the total energy transferred by the child. That's what the work done. Question 3 is out of 10 marks. Hopefully you got 10 out of 10. Well done if you did. Right, question 4. So a student investigated how the pressure of a gas depends on its temperature. And the volume of the gas didn't change, and we've got some equipment of how we carry out this investigation. Now 4.1, pressure is sometimes measured in units called atmospheres. 1 atmosphere is 10 to the power of 5 pascals. What is 1 atmosphere in kilopascals? Now this is where the prefixes become important. Well, a kilopascal means 1,000 pascals. So 1 kPa equals 1,000 pascals. So we need to divide 10 to the 5 by 1,000. That will give you the answer of 100. You might have kept it in standard form. You could also answer 10 to the power of 2. It's only worth 1 mark, but it's handy to remember the prefixes. 4.2. The student took 4 pressure readings for each temperature, and we've got the table of results when the temperature was 50 degrees centigrade. We need to calculate the uncertainty in the mean pressure. So this is, when we talk about uncertainty, we need to be calculating, basically the range. What is the range? We need to almost have the mean value plus or minus all the numbers within that range. So in this case, the range of values is 0.121 minus 0.115. That will give you a value of 0.006. Now that covers the whole range of values. Now our uncertainty has to be plus or minus that. Therefore we need to divide that answer by 2, which will give our uncertainty of 0.003 megapascals, and there's your answer. Now 4.3, we've got a sketch graph of the results, and the student said that as the temperature increases, the pressure increases. Give a better description of the relationship between temperature and pressure. Now it is true that as the temperature increases, the pressure increases. However, the bit they've missed out is the fact that the relationship is linear. So it's a straight line relationship. Now, if you talk about this being directly proportional, you will lose the mark. Although this is a straight line, which often suggests it's directly proportional, it doesn't go through the origin. That is why we have to say that this is just a linear relationship, not directly proportional. And then the next part to this question, we've got our pressure cooker is a sealed pot that uses steam to cook foods. And then you've got a diagram showing how it works. Now, when the water in the pressure cooker starts to boil, the amount of steam in the pressure cooker increases. The temperature in the steam increases above 100 degrees centigrade. We can do that because we're increasing the pressure. We need to explain why these changes make pressure in the cooker increase. Now this is worth 5 marks, and you just need to almost kind of learn this kind of answer and just step by step. And it's another good example of where you can bullet point an answer. So the first thing, as the the amount of steam increases, it means that we've got more particles of steam. So that's gone up as well. That seems pretty quite obvious. Now, as the temperature goes up, our steam particles move faster. What that means is that the particles are going to collide with the walls of the pot. These collisions are more frequent. So you're getting more collisions per second. That's what the frequency is all about. Each collision exerts a force. So basically, the pressure goes up because you just got more collisions, more frequent collisions, each delivering a force. That's why the pressure goes up. There's your 5 marks. It's worth just kind of learning this every time, and this almost links to things like your chemistry with your rate of reaction, about what happens when we increase pressure, what happens if we heat a sealed can. It's a similar kind of answer every time, so it's well worth revising that one frequently. Alright, 4.5. Now, if the pressure inside the pressure cooker becomes greater than 200 kilopascals, then some of the steam is released through the safety valve. The released steam expands as it moves into the atmosphere. Explain how a change in density of the steam is caused by a change in the arrangement of particles in the steam as it is released. Now, first of all, those particles escape. So the first thing they're going to do is spread out. So the particles spread out. There's our first mark. So it means that the steam takes up more space, takes up a greater volume. But remember, we've got the same number of particles there. So we've got the same number of particles, but taking up more space, a greater volume. And this, for your third mark, you've got to remember that density equals mass over volume. If you increase the volume, which is what we've done, it means that, therefore, your density, just going to use the abbreviation there, your density is going to go down. So that one, just think about what is happening. So the particles spread out more, they take up a greater volume. So the same number of particles in less space, the density goes down. Now, question 5, we're on to the electricity topic now. So we've got a camera in a mobile phone. It uses an LED to provide a light when taking a photograph, and the student investigates how the potential difference across an LED varies with the current in it. And then we've got the circuit shown. Now the student closed the switch. The voltmeter gave a reading of 5 volts, but the ammeter gave a reading of 0 milliamperes. The LED did not emit light. So explain how the student should have changed the circuit to make the LED emit light. Now, this is all about remembering what LED actually stands for. An LED is a light emitting diode. Now the important bit is the diode. Now a diode only allows charge to flow in one direction. So clearly what we've done here, assuming that the LED is a working bulb, we've just connected up the wrong way. So we need to get it to work, reverse the connections on the LED, because I'll finish the answer up here, because diodes only allow charge to flow in one direction. That's where you get your second mark from. Okay, next one. Back on a calculation, and again this is worth 5 marks, and again, great question if you can get your head around it, and you'll see that there's not a huge amount to write for this answer, but you can get potentially 5 marks out of it. Now, you do still have to kind of earn those marks. So here we've got students changed the circuit so that the LED did actually work, emit light. We've got a current of 290 milliamperes. We've got a power of 0.98 watts. We need to calculate the potential difference across the LED. So we need to be thinking about power, current, and potential difference. Now there's a catch here, which hopefully you've realised straight away. Our current is given in milliamperes, 290 of them. We need to convert that into amperes, into our standard units. We do that by dividing by 1,000. So divide that by 1,000, and then we'll have our current, which is 0.29 amperes. At this point, we can now start substituting numbers into our formula. Now, again, they're making you work hard here because you need to remember we've got power, current, potential difference. We need to use a formula, power equals potential difference multiplied by current. Once we've got that formula, we need to substitute our numbers in. Our power is 0.98 watts. Potential difference is what we're trying to find out, and that's multiplied by 0.29 amperes. We just need to solve for that equation now. So we need to divide both sides by 0.29. So it gives us V equals 0.98 divided by 0.29. Put those numbers carefully into your calculator and you end up with an answer of 3.79, and I think it goes on for a while. We need to go back and look at the question. Give your answer to 2 significant figures. So in this case, we're looking at, well, 3.3 are the significant figures, but we'll look at the third figure, which is a 7. It's more than 5, therefore we round up. To get our 5th and final mark, we end up with 3.4 volts. Again, it's quite limited in the writing you have to do here, but the important thing is it's picking the right equation to use, and it's just working out right which formula. So use the clues in front of you, and it comes down to practicing them. Alright, next question. So we've got a traditional camera uses a flash unit to provide light. So we've got a picture of a camera there. The flash unit emits light from xenon gas in a fluorescent tube. What happens when a xenon atom emits light? Now, this is almost as much chemistry as it is physics. What happens is when you give energy to our atoms, the electrons get excited and they jump up into higher energy levels, but they give off light when they lose that energy and drop back down to the correct energy level. That energy that they lose is released as light. So it's actually that first answer. So the electrons in the atom just fall to a lower energy level. As they lose that energy is given as light. Right, again, 5.4. This is another maths question, and this is brilliant if you get comfortable with using your formulas, and it's worth 6 marks. So we're going to have to have a good think about how we do this, but we're probably going to have to use 2 formulas. So, you know, when they have such high kind of marks for a question, they're going to make you work hard for it. Now, we've got, in our flash unit, we've got a potential difference of 200 volts. We've got a flash of light, we've got a time there, and we've got some energy there. We need to calculate the mean current. Now, if we're given a time and current, which we've got to calculate, there's a formula linking that. So we've got Q equals IT. So the charge flow is current times time. So unfortunately, we can't work that out yet because we haven't actually got the charge flow. However, this is where we need to use our potential difference and our energy, because there is a formula that links potential difference, energy, with our charge flow. It says use the physics equations sheet. In this case, we want energy transferred is charge flow multiplied by potential difference. Now, when we substitute the numbers in that we've got 1.4 joules of energy. Q, which is our charge flow, we don't know yet. That's what we want to find out. So it's just Q multiplied by 200. We need to get Q by itself, therefore divide both sides by 200. And we've got 1.4 divided by 200. That then gives us 0.007, and it's coulombs, which is a capital C. Right, so at this point, we now need to go back to what we were looking at before. The fact that charge flow, Q, equals current multiplied by time. If we substitute in the numbers that we've got 0.007 equals our unknown current, I, multiplied by time, which is in standard form, 2.8 times 10 to the minus 4. So we now need to get I by itself, so we do that by dividing both sides by the 2.8 times 10 to the minus 4. So the numbers we put into our calculator are 0.007 divided by 2.8 times 10 to the minus 4. And when you put those numbers in, you come out with a nice number of 25 amperes. Now, that would get you the 6 marks, and you got all the working out there. It doesn't look an awful lot of writing for 6 marks, but there is actually quite a lot of physics in there. And it's just getting comfortable trying to work out what are the 2 formulas that we need to use. But if you can get comfortable doing this, it's a nice 6 marks to pick up. Right, question 6, we're on to radioactivity now. So we've got a smoke detector, contains a source of alpha radiation in a plastic case. The question now is, a source of beta radiation in a smoke detector would be more hazardous than a source of alpha radiation. I'll explain why. Well, if you remember, beta is more penetrating, and it can travel further in the air. Alpha particles can only travel a few centimeters. Beta particles can travel, a few meters. So the fact that the beta is more penetrating, so it means that the beta radiation could irradiate people just walking past the detector. That's the second mark. And then 6.2, we've got actinium is one source of alpha radiation. An actinium nucleus emits an alpha particle and turns into a francium nucleus. And here we've got the nuclear equation. We need to determine the values of A and Z. Now, the important bit here is to remember that an alpha particle is the equivalent of a helium nucleus. So that means that it contains 2 positively charged protons and 2 neutral neutrons. The 2 stands for the 2 protons, the 4 is the mass of 2 protons and 2 neutrons. The first thing I would do in this question is to fill in your 4 and 2 on your alpha particle. You're not going to get any marks for that. You then just need to work backwards. Our actinium nucleus is lost 2 protons and forms a francium nucleus of 87. 87 plus 2 will give you 89. So that would be the proton number, which is Z. And then of course we've got a mass of 4 has been lost from the 223. You just need to add those 2 numbers together and that will give you A. So in this case it would give you 227. Not really sure why they give you all this space, but I'd almost do the working out actually on the equation. Right, 6.3. Now a teacher wants to find out what nuclear radiation is emitted from a source. Now the teacher placed different barriers between the source and its detector. The teacher recorded the count 30 seconds after each barrier was put in place. Explain what nuclear radiation was emitted by the source. Now this is worth 4 marks. So there's probably a bit of work to think about in this one. So we start off with no barrier. We have a high count of radiation. Now we stick a piece of paper in front of our source and we reduce the count rate significantly. Now you've got to remember that paper is very good at stopping alpha particles. So this is suggesting that our count rate has dropped because there's alpha particles there that are no longer getting through the paper. However, there is still some radiation there. But when we put the aluminium sheet there, our count rate drops to 0. Now if you remember, this is 5 millimeters of aluminium, so it's a reasonably thick sheet of aluminium. If you remember, it only takes 2 to 3 millimeters of aluminium to stop beta particles. So this is suggesting or telling us that this source also contains beta particles. Now the fact that we don't have any count rate after the aluminium, it means that this source certainly doesn't contain gamma, is not releasing gamma rays. Remember, lead is what we need to block gamma, but there's certainly no gamma rays in that particular source. So to get our 4 marks, we need to talk about that some radiation is stopped by paper. This means we've got alpha radiation definitely being emitted. And then that's your first 2 marks. The next 2 marks come from the fact that some radiation passes through paper but is blocked by aluminium. That tells us we've definitely got some beta particles being released by that source. There's your 4 marks. Okay, and then we're on to the final question now. So here we've got a graph showing the activity of 4 different radioactive isotopes, A, B, C and D, and how they change over time. You need to write the isotopes, A, B, C and D, in order of increasing stability of their nuclei, and then you need to be explaining your answer. So you're going to get 1 mark for putting the sources in the correct order, and then you get the 2 marks for the explanation. Now, with this one, it's almost better to start off with the explanation, and that will tell us the order from there. So a substance with a longer half-life is more stable. So what we're doing is our answers, which we're going to do now, are in order of increasing half-life. So what I would do with this question is I'm now going to calculate the half-life. So if we take sample A, we're starting at 400, we need to go to 200. So if we do a line across there and go down, that's going to give us a half-life for sample A of probably, I'd say that's probably about 17.5 years. Now I need to do the same thing for B. Now B starts at 250, so we half that to 125. So it takes us along to about here. Oh, a bit wobbly. I'd say that's around about 12 years. We'll then look at source C. Well, that starts at 100, and we need to see where it gets down to 50. Well, it doesn't even get down to 50 within the graph. I think if you continue that line, it might do it by about 25 years. So quite a long half-life. And then finally D starts off at 150 and it goes to 75. So we need to make sure we're hitting D. So draw that line across to hit D, and we're getting, say 7.5 years. So those are our half-lives. Remember, the most stable has the longest half-life. So that will give us C. And then of course it would be A, and then B, and D is the least stable. And there's our 3 marks. So that is the end of that exam. So that question is, I think, is out of 11 marks, and the total exam is out of 70. So add up your score now and see how well you've done.